In this video, we will cover equations that relate equilibrium to thermodynamics. We will also revisit an equation that we covered in previous videos, but this time it will be applied to equilibrium. This equation relates temperature changes to equilibrium constants. Equilibrium is one way to look at reactions. Another way is thermodynamics. The variable to use in equilibrium is the equilibrium constant value, which equals the concentration of the products divided by the concentration of the reactants at equilibrium. Another important variable for equilibrium is the reaction quotient, which also equals the concentration of products over the concentration of reactants. It is just measured at any point in the reaction and doesn't have to be at equilibrium. The variable to understand in thermodynamics is delta G, which is Gibbs free energy. It is the available energy to do work for a reaction. The equation that relates delta G to the reaction quotient is delta G equals delta G standard plus the gas constant, R, times the temperature, T, times the natural log of Q. The standard delta G is just measured at standard conditions, which is usually 1 atm for gases and 1 molar concentration of aqueous solutions. R, the gas constant, has a value of 8.314 joules per mole times Kelvin, and the temperature must be in Kelvin. If delta G is less than 0, then the reaction is spontaneous. If delta G is greater than 0, then the reaction is non-spontaneous. If delta G equals 0, then the reaction is at equilibrium. If delta G equals 0 and the reaction is at equilibrium, then we know we need to use the variable of K, not Q. Let's plug these things into the equation delta G equals delta G standard plus the gas constant R times the temperature T times the natural log of Q. Delta G equals 0, which equals the standard state delta G plus R times T times the natural log of K, because we are now at equilibrium. If we rearrange this equation, we find that the standard delta G equals negative gas constant times temperature times the natural log of the equilibrium constant. Now rearrange this equation to solve for K, and we have the natural log of K equals the negative standard delta G divided by R times T. And then take the exponential of both sides, and we have K equals the exponential of negative delta G standard divided by R times T. All of these equations are very important to understand for this discussion of equilibrium and thermodynamics. We know that if K is greater than 1, the reaction is product-favored, and if K is less than 1, the reaction is reactant-favored. This certainly is related to the delta G standard for a reaction. If K is greater than 1, then the natural log is positive, and the delta G standard is negative. If K is less than 1, then the natural log is negative, and the delta G standard is positive. This goes back to our discussion of delta G values and spontaneity of reactions. If standard delta G is less than 0, then the reaction is spontaneous, and it will proceed in the forward direction or be product-favored. If standard delta G is greater than 0, then the reaction is non-spontaneous, and it will proceed in the reverse direction or be reactant-favored. There are two equations to review for calculating delta G. The first is delta G equals delta H minus temperature times delta S. Or you can use this same equation to calculate standard delta G. Then it becomes standard delta G equals standard delta H minus temperature times standard delta S. To calculate standard delta G of a reaction, use the equation the sum of the products, standard delta G of formation, times the coefficient in the balanced equation, minus the sum of the reactants, standard delta G of formation, times the coefficients in the balanced equation. You can also calculate the standard delta H of a reaction and the standard delta S of a reaction using the same type of equation. Just substitute in the standard delta H formation values and the standard S values respectively. In all of these equations, the N and M variables are the coefficients of the individual products and reactants in the balanced equation. All the values that are in the appendix of your textbook are standard delta H of formation, standard S, and standard delta G of formation values. Let's derive an equation relating K to standard delta H, temperature, and standard delta S. We will use two equations we have already mentioned in this video. The first is standard delta G equals standard delta H minus temperature times standard delta S. The second is the natural log of K equals the negative standard delta G divided by gas constant times temperature. Plug in the standard delta H and standard delta S equation into the K equation, and we find that the natural log of K equals negative standard H divided by R times T plus temperature times standard delta S divided by R times T. This equation is the natural log of K equals the negative standard delta H divided by R times 1 over temperature plus the standard delta S divided by R. If you graph the natural log of K versus 1 over temperature, we have a straight line, with the slope equal to standard delta H divided by R, and the y-intercept equal to the standard delta S over R. If we have two different temperatures and we are trying to find the K value at another temperature, we can utilize the two temperature versions of this equation in which the standard delta S over R term drops out. This equation looks like the natural log of the equilibrium constant 2 over the equilibrium constant 1 equals the negative standard delta H divided by R times 1 over temperature 2 minus 1 over temperature 1. This equation is called the Van Hoff equation and was named for Jacobus van Hoff, a Dutch chemist who won the first Nobel Prize in chemistry. Now let's work on some problems using the concepts described in this video. 1. Calculate delta G for the following reaction: CH4 gas plus H2O gas in equilibrium with 3H2 gas plus CO gas at 298 Kelvin if standard delta G equals 142.15 kilojoules per mole and A, the concentration of CH4 equals 0.50 molar, the concentration of H2O equals 0.40 molar, the concentration of H2 equals 0.90 molar, and the concentration of CO equals 0.070 molar, and B, the concentration of CH4 equals 0.050 molar, the concentration of H2O equals 0.070 molar, the concentration of H2 equals 0.60 molar, and the concentration of CO equals 0.20 molar. Is the reaction spontaneous in each of these cases? To calculate the delta G, given the standard delta G and the concentration of reactants and products, we need to use the equation delta G equals delta G standard plus the gas constant R times the temperature T times the natural log of Q. First, write the reaction quotient expression, which for this reaction equals the concentration of H2 cubed times the concentration of CO divided by the concentration of CH4 times the concentration of H2O. For part A, plug the values into the Q expression, and we have 0.90 cubed times 0.070 divided by 0.50 times 0.40, which equals 0.2552. Now let's consider units. We have our standard delta G in kilojoules per mole, and the gas constant is in units of joules per mole times Kelvin, and our temperature is given in Kelvin. Let's convert our gas constant to kilojoules per mole times Kelvin so we can calculate our answer in terms of kilojoules per mole by dividing 8.314 by 1,000. We have 8.314 times 10 to the negative 3 kilojoules per mole times Kelvin. Now let's plug our values in to solve for delta G. Delta G equals 142.15 kilojoules per mole plus 8.314 times 10 to the negative 3 kilojoules per mole times Kelvin times 298 Kelvin times the natural log of 0.2552. Our delta G equals 138.8, or to two significant figures, 140 kilojoules per mole. This reaction is not spontaneous because the delta G is greater than 0. For part B, calculate the Q value for this part of the question. The Q expression is again the concentration of H2 cubed times the concentration of CO divided by the concentration of CH4 times the concentration of H2O. Plug the values into the Q expression, and we have 0.60 cubed times 0.20 divided by 0.050 times 0.070, which equals 12.34. We will leave our R value as 8.314 times 10 to the negative 3 kilojoules per mole times Kelvin. Now solve for delta G. Delta G equals 142.15 kilojoules per mole plus 8.314 times 10 to the negative 3 kilojoules per mole times Kelvin times 298 Kelvin times the natural log of 12.34. Our delta G equals 148.4, or, to two significant figures, 150 kilojoules per mole. This reaction is not spontaneous because the delta G is greater than 0. 2. Calculate standard delta G of reaction for the formation AgCN2 negative at 25 degrees Celsius if the K of the formation equals 1.0 times 10 to the 21st. Is the reaction spontaneous under these conditions? To calculate the standard delta G of the reaction given a K value, use the equation standard delta G equals negative gas constant times temperature times the natural log of the K value. Again, let's think about the units of this question. The gas constant is in terms of joules per mole times Kelvin, so the temperature needs to be in Kelvin. 25 degrees Celsius plus 273.15 equals 298.15 Kelvin. Then plug what you know into the equation. Standard delta G equals negative 8.314 joules per mole times Kelvin times 298.15 Kelvin times the natural log of 1.0 times 10 to the 21st. Standard delta G equals negative 1.199 times 10 to the 5th, or, rounded to two significant figures, negative 1.2 times 10 to the 5th joules per mole. Since this delta G is a large negative number, it is much less than 0, this reaction is definitely spontaneous. 3. Calculate K for a reaction at 25 degrees Celsius if standard delta H of the reaction equals negative 25.0 kilojoules per mole and standard delta S of the reaction equals negative 875 joules per mole times Kelvin. Is this reaction reactant-favored or product-favored? To calculate K for a reaction given standard delta H and standard delta S, we could either solve for standard delta G and then solve for K using the equation given in the last question, or we could use the combined equation, the natural log of K equals the negative standard delta H divided by R times 1 over temperature plus the standard delta S divided by R. We will use the combined equation, but either way we will get the same answer. Let's talk about units. The standard delta H is given in kilojoules per mole, and the standard delta S is given in joules per mole times Kelvin. Since the gas constant is also in joules per mole times Kelvin, let's convert delta H into joules per mole. Delta H equals negative 25,000 joules per mole. Then we need to convert temperature to Kelvin. 25 degrees Celsius plus 273.15 equals 298.15 Kelvin. Then natural log of K equals negative 25,000 joules per mole divided by 8.314 joules per mole Kelvin times 1 over 298.15 Kelvin plus negative 875 joules per mole times Kelvin divided by 8.314 joules per mole times Kelvin. The natural log of K equals negative 95.16, and K equals 4.71 times 10 to the negative 42nd. Since the K value is much less than 1, this reaction is highly reactant-favored. 4. Use the data in the table to calculate the value of K at 25 degrees Celsius and 1500 Kelvin of the following reaction. Cl2 gas plus N2O4 gas in equilibrium with 2NO2Cl gas. Is the reaction reactant-favored or product-favored at these two different temperatures? To calculate the value of K at 25 degrees Celsius, use the standard delta G of formation values to calculate the standard delta G of the reaction, and then use the equation K equals the exponential of negative standard delta G divided by R times T. To find the standard delta G of the reaction, use the equation the sum of the products, standard delta G of formation, times the coefficients in the balanced equation, minus the sum of the reactants, standard delta G of formation, times the coefficients in the balanced equation. This will equal 2 moles times 54.39 kilojoules per mole minus 0.00 kilojoules per mole plus 1 mole times 97.82 kilojoules per mole. Our standard delta G equals 10.96 kilojoules. To solve for our K value, let's consider units. Since we have our delta G and delta H values in kilojoules, let's convert our R values to kilojoules. This will equal 8.314 times 10 to the negative 3 kilojoules per mole times Kelvin, and our temperature also needs to be in Kelvin. 25 degrees Celsius plus 273.15 equals 298.15 Kelvin. And then our K equals the exponential of negative 10.96 kilojoules divided by 8.314 times 10 to the negative 3 kilojoules per mole times Kelvin times 298.15 Kelvin. Our K equals 0.0120. This reaction is slightly reactant favored because it is less than 1. To calculate our K value at a different temperature, use the equation, the natural log of equilibrium constant, 2, over equilibrium constant 1, equals the negative standard delta H divided by R times 1 over temperature 2 minus 1 over temperature 1. In this case, we will consider the 298.15 Kelvin set of conditions, 1, and the 1500 Kelvin set of conditions, 2. Then we need to calculate our standard delta H of the reaction. We will do this using the same equation we used to calculate our standard delta G of the reaction. Standard delta H of the reaction equals sum of the product's standard delta H of formation times the coefficient in the balanced equation minus the sum of the reactant's standard delta H of formation times the coefficients in the balanced equation. This will equal 2 moles times 12.55 kilojoules per mole minus 0.00 kilojoules per mole plus 1 mole times 9.16 kilojoules per mole. Our standard H of reaction equals 15.94 kilojoules. We will still express our R values in terms of kilojoules as 8.314 times 10 to the negative 3 kilojoules per mole times Kelvin. Then plug everything into our equation. We have natural log of our unknown K divided by 0.0120 equals negative 15.94 divided by 8.314 times 10 to the negative 3 times 1 over 1500 minus 1 over 298.15. Solve for the right side of the equation first, and we have 5.152. Then take the exponential of both sides, and we have our unknown K divided by 0.0120 equals the exponential of 5.152. Then our unknown K equals 0.0120 times the exponential of 5.152, which equals 2.07. This reaction becomes product favored at this higher temperature because our K value is greater than 1.